All right. In this video, we're going to go over some past exam questions from exam 3, which is the acid-base exam. Okay, so let's begin. All right, the first question. Valproate is used to treat epilepsy. What would happen to the equilibrium of valproate in water when NaOH is added to the system? Okay, so let's take a look at this problem. Right, so valproate is the conjugate base of a weak acid. Okay, so what we have is a minus here, which came from a carboxylic acid. Okay, and then when this reacts with water, when this is in water, it's going to achieve this equilibrium, AQ plus OH minus AQ. Okay, and if you add NaOH, what this means is you are adding OH minus. Okay, so you add OH minus, that means it's going to increase the OH minus concentration. Right, let me have a different thing. So you will be increasing the concentration of OH minus. Okay, and then if you look at the kinetic argument, when it comes to kinetic argument, it's all about the forward rate versus the reverse rate. When it is at equilibrium, forward and the reverse rate are equal to each other. But because of this perturbation, you're going to increase one of the products. Okay, and as a result of that, okay, so if you write rate reverse, it's going to be K reverse times HA concentration times OH minus concentration, and rate forward is K forward is K forward times A minus concentration. And what you're doing is you are increasing the concentration of OH minus, and that's going to affect the reverse rate. It's going to increase the reverse rate, and as a result of that, our reverse rate will be greater than the forward rate. Therefore, we should produce more reactants until the forward rate becomes equal to the reverse rate again. Okay, so let's pick the answers. It has to be between the first two. Okay, and we know that the reverse rate must be greater than the forward rate. Therefore, the last two options are out. And then the equilibrium should shift to reactants, not products. Therefore, option B is out as well. Okay, so the correct answer is option A. Right, so let's mark that and move on to the next question. So in this question, you're given a percent species diagram, and you are asked to calculate the Kb value. Okay, and we know from the percent species diagram, at the 50% mark, that means we have 50% of conjugate base and 50% of the weak acid. It's going to give the pH is going to become equal to pKa. Therefore, if you go to this curve, the 50% mark, and draw a line, then if you read the pH value at that point, which is around, I don't know, let's say 3.4, close to 3.5, 3.4. So your pKa is equal to 3.4. Okay. Now the question is asking for the Kb of the conjugate base. We know that for conjugate pairs, pKa plus pKb is equal to 14. Therefore, pKb is equal to 14 minus 3.4, which is going to be 10.6. Okay. Therefore, Kb is 10 to the power of minus 10.6. Okay, so that should be closer to this option D over here. So I would select option D. Let's go back to the question and then select option D. Next page. Question 3. You are given a molecule, and then you are asked to determine what is dominant when you have this molecule in water. Okay. Again, what you're given is acid. How do you know it's an acid? Because we see that we have a carboxylic acid group over here. And if that is the case, it's going to act as an acid, weak acid. Okay, so weak acid, that's the most important thing. Okay, so if it's a weak acid, so let's call this HA. I'm going to call this HA, right? When you put this in water, it's going to establish this equilibrium. H3O plus AQ plus A minus AQ. Okay. Now it's gonna, as a result of this, it's gonna increase H3O plus concentration, and that's what makes an acid, right? Now the question is, what will we have in higher concentrations? Will we have the HA or A minus in a higher concentration? Now, the caveat here is we know it's a weak acid. Weak acid means it's going to be a partial dissociation, okay? And then the K value for this will be less than 1. If the K is less than 1, that means you have a greater denominator. That means you have more of the reactants than of the products, okay? So between HA and A minus, all right, HA concentration will be greater than A minus concentration, okay? So anything with a charge is out. Option A, option B, C, D, and E are out. Okay, because I mean, you know that we need to have a higher concentration of the weak acid, which is neutral, right? And then in both cases, we have C6H9 O2F and C6H9 O2F. Okay, therefore it must be the same species. Now all we have to decide is think about OH minus and H3O plus, because that's the only difference there. Now, since it is an acid, it's going to increase the H3O plus concentration. Therefore, the H3O plus concentration must be greater than the OH minus concentration, right? And therefore, the correct answer must be option D. Right, let's go back to this and select option D. All right, let's tackle this problem. Select the highest concentration, or select the dominant form of the molecule if the pH is set to 1.2. Okay, and then again, first thing I would do is we will think about what these pKa values correspond to, what functional groups. All right, so if we have pKa in 9.6, right, so between carboxylic acid groups and in NH2, you know that it should be corresponding to the NH2 group. So for NH2 group, pKa must be 9.6. It's going to be weakly acidic, the weakest acid here. Okay, and then between the carboxylic acid groups, the one that is closer to the electron withdrawing NH2 should be more acidic. Therefore, that should have the lowest pKa. So this should have a pKa of 1.9, and then the other guy will have a pKa of 3.7. Now we know that. Now all we have to do is we have to compare our pKa values to the pH, right? So when it comes to the amine group, our pH 1.2 is less than 9.6, which is our pKa. Okay, if the pH is less than the pKa, we know that the acid is dominant. Okay, and if we go to the next carboxylic acid group, the most acidic one, our pH is 1.2, which is less than the pKa of that. Therefore, the acid is dominant. And then when you go to the last one over here, again, our pH of 1.2 is less than 3.7, which is the pKa of this carboxylic acid group. Therefore, the acid is dominant. Okay, acid form of NH2 is NH3 plus. Okay, the acid form of carboxylic acid is COOH. Okay, so we have two COOH groups and one NH3 plus groups in our molecule. Okay, so first one is out, and then the second one is out. The third one is out. I would go with the fourth one over here, where we have NH3 plus and COOH. Okay. Let's see. So the correct answer is this one. All right, moving on to question 5. Rank the predicted acid strength, weakest to strongest in these molecules. Okay. When it comes to this, we go with the features. Feature 1, the charge bearing atom. Feature 2, the charge delocalization, and feature 3, the inductive effect on the neighbors. Now, in these 3 molecules, the most acidic proton in each of the molecule is the first thing we need to decide. So in the first molecule, we can see that it has to be this hydrogen over here. In the second molecule, it has to be this hydrogen bound to oxygen. The third molecule, it has to be this hydrogen bound to oxygen. You have hydrogens bound to carbon, but we know based on feature 1, hydrogen bound to carbon is going to be the least acidic compared to hydrogen bound to more electronegative atoms like nitrogen and oxygen. Okay. Based on feature 1, we know that the least acidic nitrogen has to be the one on A based on feature 1, because feature 1 says if they are in the same period, then having the negative charge on the more electronegative atom is more stable. So removing this proton will give us a negative charge on nitrogen, oxygen, and oxygen in the third one. Okay, so having the negative charge on nitrogen is the least stable situation. Therefore, A is the weakest. Therefore, we can get rid of options C and D. And then between B and C, then we move on to feature 2. Feature 2 is the charge delocalization. In both cases, you have a double bond, one bond away from the negative charge. Therefore, you can have charge delocalization or resonance stabilization in both cases. So feature 2 doesn't cut it. And then we move on to feature 3, which is the inductive effect of the neighbors. If you have neighbors that can withdraw the electrons, that's going to reduce the negative charge or negative electron density. The electron density of the anion, stabilizing it. And we can see that we have this fluorine over here, which is an electron withdrawing group. Okay, and because of this neighbor, we can assume that we can think that the molecule B has to be the most acidic, because the conjugate base of molecule B should be more stable. Should be the most stable compared to the other 3. Okay, so B is the strongest, so I would go with option A. Right, option A. Question 6, given the Ka for this reaction, right? You are asked to calculate the pKb for the conjugate base reaction with water. Okay, so now you're given the pKa for this acid dissociation. Okay, and then you're asked to find the pKb if this amine of the conjugate base reacts with water. In other words, we need to find the pKb for the conjugate base. Okay, so we know for conjugate pairs, pKa plus pKb is 14. pKa plus pKb is 14. Now we have the Ka, so from that we can calculate the pKa, okay, which is minus log of this value. So if I calculate that, the minus log of 2.1 times 10 to the power of minus 5 is 4.7. Okay, 4.7. And then therefore the pKb must be 14 minus 4.7. 14 minus 4.7, which is 9.3. Okay, now for the Kb must be 10 to the power of minus 9.3. Let's do that as well. 10 to the power of minus 9.3 is 5 times 10 to the power of minus 10. 5 times 10 to the power of minus 10. So we can go with that as our answer. 5 times 10 to the power of minus 10. Oh, you know what? I mean, you don't have to do that. I should be asking for PKB. You don't have to do this step. Okay, we're done with this. Done at this step. They're asking for the PKB, 9.3. Right, so the correct answer is 9.3. Right, so you go here and type 9.3 and done. All right, so question 7, you're given a base. Oh no, give me a second. You're given a molecule. Now what they're asking you to make, do a modification to make this a stronger base. Okay, so the most basic center in this molecule is in the middle. Okay, this part over here is the most basic center. Again, because it is feature 1, 2, and 3. Okay, so if you look at the first point over here, so we want to make it a stronger base. Okay, you replace the hydrogen with an OH group. When you do that, what you're doing is you have to changing a neighbor. That's the only thing you have done there. When you change the neighbor with the more electron withdrawing one, so electron withdrawing neighbors stabilizes the base, making the lone pair less available to grab a proton. So it's going to make it a weaker base. So this is out because this electron withdrawing group is going to stabilize the base, making it a weaker base. Option 2. Now what we have done is we have replaced the hydrogen with a CH3 group. Now we know that what we have done is we have converted a secondary amine, which is the 4th feature we have considered for the bases, with a tertiary amine. Tertiary amines are always weaker than the secondary amines. For that reason, option B is out. Option C, the difference here is we have a chlorine. We have replaced a methyl group here with a chlorine atom over here, which is electron withdrawing. So we have a neighbor now, which is electron withdrawing. Electron withdrawing neighbors are always stabilized in the bases, making them less basic or weaker. So therefore, that is out as well. And option D has to be the correct answer. Let's see why. The only difference is we have got rid of this double bond over here. Okay, so there was this double bond, and now it is gone. Now, what this double bond does is feature 2. Now, when you have a double bond, one bond away from the lone pair, you can have charge delocalization. Okay, the charge delocalization or resonance that stabilizes the base, okay, making it a weaker base. Now, if you take away that double bond, you're going to take away that charge delocalization or resonance stabilization, making it a stronger base. So therefore, the correct answer is option D. Okay, so let's mark that. Option D is the correct answer. Question 8, you are given a molecule, non-steroidal anti-inflammatory drug, starting with an aqueous solution of flurbiprofen. Which of the following graphs represents the change in pH and the reaction quotient as a function of time if if the conjugate base or C15H12FO2 minus is added to the system? Okay, and you can see that. Okay, so this is an acid because of this carboxylic acid group. So I'm going to call this an HA. Okay, and now which has a chemical formula of H13FO2. Now, if we go to this molecule over here, you can see that one of the hydrogen is missing, and then you have a negative charge, which is characteristic of the A minus. So this should be A minus. Okay. Now, if you have an aqueous solution of this molecule, and that's going to establish this equilibrium with water, H3O plus AQ plus A minus AQ. Okay. Now, if you what they're doing here is they're adding A minus. Okay, you're going to increase the concentration of A minus. Okay, so if we add A minus, you're going to increase the A minus concentration. Okay, because you know that Q reaction quotient is H3O plus concentration times A minus concentration divided by the reaction concentration, which is HA concentration. So if you are increasing the A minus concentration, you're going to increase the numerator compared to the denominator, and as a result of that, your Q is going to be greater than K. Right? So when your Q is greater than K, then we know that options A and C are out, because in those options they are saying that Q is going to decrease. No, Q has to increase because you are increasing the numerator. And then what this is going to do is the Q is going to come down. Q needs to decrease to come down to K value. To do that, our products needs to be converted to reactants. That means H3O plus will be, which H3O plus, which is a product, will be consumed to produce more reactants. And as a result of that, H3O plus concentration should decrease. H3O plus concentration decreases, pH increases. Okay, so therefore the correct answer is option B. All right, so let's select that and move on to question 9. So you're given an equilibrium and asked the reaction direction. Okay, so whenever you're given a problem like this, what we do is we look at, so this is an acid-base reaction. When you are given an acid reacting with base, and you ask the question whether this reaction is product favored or reactant favored or the reaction direction, what we learned in class was to focus on the base. One with the most stable base will be favored over the other. Now, the basis of these reactions are, in the reactant side, it has to be this with the negative charge, because it cannot act as an acid because of its negative charge. And on the product side, it has to be this. Now, in both cases, if you consider feature 1, you have the negative charge on oxygen. Therefore, feature 1 doesn't cut it. There's no difference in the charge-bearing atom. But when it comes to feature 2, in the reactant side base, you have a double bond, one bond away from the negative charge. Therefore, this charge will be stabilized due to resonance or charge delocalization. So we don't know how to go further. Based on feature 2, this should be more stable. Reactant side base should be more stable than the product side base. Therefore, our reaction will be reactant favored. Okay, so the correct answer must be not product favored. It should be reactant favored, because the weaker base is in the reactant. Weaker base means more stable base. Okay, therefore the correct answer is option B. All right, so correct answer is option B. Moving on to question 10, you are given a molecule. You are given the H3O plus concentration. You are asked to find the QOH. Okay, so this is one of the straightforward questions. So you know the H3O plus concentration. Okay, you know the pH is minus log H3O plus concentration, which is minus log 0.043. Right, so if you go back, minus log 0.043 is 1.36. 1.36. Yeah, and then what we're going to do is, yeah, then what we need to do is, we know that the pH plus pOH is equal to 14 at 25 degrees Celsius. Therefore, pOH is 14 minus 1.36. Okay, so that is going to be 12.64 should be your answer. Okay, so go here and type 12.6. See if that's, if DeepL can accept that answer. Next page. Question 11, you're given a molecule. Okay, it's a base. How do you know it's a base? Because you have this amine group over here. Okay, and then you're given the initial concentration of that, which is the C node, and then you're given the pKb, right? And then you also calculate the pH. Okay, so we know if it's a base, it's a weak base, because amines are weak bases. OH minus concentration is initial concentration times Kb, square root of that. Okay, and therefore, if we plug them in, we're gonna get C node 0.018 times Kb, which is 10 to the power of minus 4.8, and then take the square root of that, and that should give you the OH minus concentration. Let's do that. Okay, so the square root of 0.018 times 10 to the power of minus 4.8 is I got 5.34 times 10 to the power of 1, 2, 3, 4 minus 4 as my OH minus concentration. So with this, we can calculate pOH, which is minus log OH minus concentration. Okay, so if we do that, let's see if I can do this together here, minus log, yeah, if you do that, you're gonna get 3.27, we can call it 3.3, and then the pH must be 14 minus pOH, which is 3.3, and that's going to turn out to be 10.7. Okay. All right, let's go and enter that answer. 10.7. Right. Moving on, question 12. You are given a molecule which has both an amine and a carboxylic acid group, right? And you're given the pKa and pKb values. Based on the pKa value, 3.7, that should correspond to the carboxylic acid, and then the pKb should be corresponding to NH2. And the question is, using the above information, select the equilibrium corresponding to a pKb of 10.3. Now, we're not talking about the amine group here for sure, because amine group pKb is in 3.3. So we must be referring to the conjugate base of the COOH group, because we know that the pKb for the conjugate base here must be 14 minus 3.7, 14 minus 3.7, which is going to be 10.3. Okay, so again, the if you're referring to that, the conjugate base of the carboxylic acid must be COO minus group. Okay, so that should have almost the same formula as this molecule, but minus one hydrogen atom. Therefore, hydrogen should be 16 NO2, and also there should be a minus charge. So we need to start with that species over here. C9 is 16 NO2 minus. And then also, since we're talking about the pKb, it needs to correspond to a reaction that produces OH minus. So therefore, option B is out. And then if you look at this, the only species, only option that has C is 16 NO2 minus as a reactant is option C. So that must be your answer. Okay. The other answers does not make sense. For an example, in option A, you have -2 charge in the product side, and the reactant side is 0, neutral. Charges don't balance, therefore this is not even a valid chemical reaction. And then when it comes to the other reaction over here, that shows you the acid dissociation of no, not acid dissociation. No, it just does not make sense. It is showing the base, the NH2 group reaction with water, because you can see that it has gained a proton. Okay, so that must be due to gaining a proton by NH2, so which is not the case here. Okay, so that is out as well. So the correct answer is option C. All right, moving on. Another reaction, then you asked to find the reaction direction and the reason behind that. Again, we will be looking at the more stable base. Okay, so bases here are the neutral species, cannot be with the positive charge. If you have a positive charge, they cannot gain another proton with a positive charge. Okay, they're going to repel. Therefore, the neutral species must be our bases in both sides. Okay, now we can see that in both cases there are amines, and then we need to go in sequence from feature 1 to feature 3 to decide which one is more stable. Now, since in both cases we have the lone pair on a nitrogen, okay, so the feature 1 doesn't cut it, and then we look at the feature 2. In the reactant side base, you have a double bond, one bond away from the lone pair. Therefore, it can be delocalized like that, or the resonance stabilizes that lone pair, which is going to make it less available to grab a proton. Okay, so because this is more stable, and then you don't have that in the product side base, because the reactant side base is more stable, it's going to be weaker than the more stable than the product side base. Therefore, reaction will be, we can expect the reaction to be reactant favored, because we have the most stable base on the reactant side. Reaction is not product favored, should be reactant favored, because weaker base is in the reactant. So this is the correct answer. Option B. Right. Now, this question is about a buffer, right? Whenever we are dealing with the buffer calculation, we know that we use the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log conjugate base concentration over the weak acid concentration. Now, from this, we can say that since they're asking for the ratio between the conjugate base and the weak acid, we can rewrite this. A minus over HA should be equal to pH minus pKa. Okay, therefore A minus over HA concentration must be equal to 10 to the power of pH minus pKa. This is what we need, right? You are given the Ka. From the Ka, you can calculate the pKa. Okay, so the pKa must be minus log 4 times 10 to the power of minus 4, which is 3.4. Okay, Ka is 3.4, and then you are given the pH, which is 5.2. We just plug in these values to find the A minus to HA ratio. If we do that, we have 10 over here. The pH is 5.2, and the pKa is 3.4. Okay, and this should be 10 to the power of 1.8. Okay, 5.2 minus 3.4 must be 1.8. Yeah, let's go with that. Okay, and then 10 to the power of 1.8 is 63. And this is equal to 63. What this means is for every 1 molecule of HA, the weak acid, you have 63 ions of A minus. Okay, you have more conjugate base. Okay, so if you look at the answers, HNO2 is the weak acid. Okay, and then NO2 minus is the conjugate base. So therefore, the only answer that corresponds to our calculation is option B. All right, the others do not match. Okay, so let's go with option B. All right, moving on to question 15, you are given a molecule, which is an acid, and then you asked to calculate the pKa. Okay, let me see. It's an acid because we know we have a carboxylic acid group. Okay, it's going to be an acid, right? And then for that, you are given the initial concentration, which is our C note, and then you are given the pH as well, right? So we know that Strio plus concentration is 10 to the power of minus pH, so it should be minus 6.4. Okay, and we also know that Strio plus concentration for a weak acid is C naught times Ka square root of that. Okay, we also find the pKa now. Okay, now we can rearrange the equation to say C naught times Ka is equal to, if you square both sides, I'm going to get rid of the square root on the on the right hand side. Then I'm going to get C naught times Ka is Strio plus concentration squared. Okay, therefore Ka must be Strio plus concentration squared divided by C naught. Now we just need to plug and chalk because we know Strio plus, which is 10 to the power of minus 6.4. Okay, and then we know C naught, which is 0.018. Okay, so this is equal to 10 to the power of minus 12.8, because 6.4 times 2 is 12.8 divided by 0.018. Let's do that calculation. Okay, 10 to the power of minus 12.8 divided by 0.018. 0.018 is 8 11.8 times 10 to the power of minus 12. Okay, so that's our Ka value. Now for the pKa must be minus log of that. Okay, now let's see if we can do that here. Minus log of 10 to the power of 10, this value is 11.1 maybe 0.5 1.1. Yeah, let's go with 11.1. Right, so we go back to the quiz and then we're going to type 11.1 and we move on. Right, question number 16. You're given the pKa and it's the same question as before, but right now it's more direct because the question is referring to pKa of 3.7. Okay, pKa 3.7 must be due to this. Okay, and then we know that it's an acid, right? So when this reacts with water, it's gonna lose the proton. It's gonna establish this equilibrium. H3O plus A minus. Okay, so what's going to happen is we're going to start with the neutral species. Okay, and then that is going to eliminate options B and C. And then we are looking at a pKa, or therefore acid dissociation. Okay, so you cannot have OH minus when we talk about acid dissociation. Acid, when they dissociate, they produce H3O plus, not OH minus. Therefore, option D is out as well. The only remaining answer is option A. Okay, and you can see that when you go from the reactant to product, we have lost one proton, and then with a minus charge. Okay, 17 became 16 with minus charge, which is corresponding to our conjugate base, which is our correct answer. So correct answer is option A. All right, last question. And you are given select two molecules. You are asked to find the most acidic molecule and the rationale behind that. Again, so this is about the three features, right? So we go with feature one. So the more acidic proton must be this hydrogen bound to go here. Hydrogen bound to sulfur and hydrogen bound to oxygen, because you have hydrogen bound to carbon, but compared to hydrogen bound to carbon, having the hydrogen on oxygen is going to be more stable. Okay, and then that's why it's going to be more, B is going to be more acidic than any hydrogen bound to carbon. But when you go down a group, right, oxygen and sulfur are in the same group. When you go down a group, the size of the atom increases. When the size of the atom increases, the stability of the anion increases because of the ordering effect on water molecules will be less. It's an entropic effect. Okay, for that reason, based on feature one, molecule A is going to be more acidic. Okay, the reason is having the negative charge on sulfur is more stable than having the negative charge on oxygen, because sulfur is larger. When sulfur is larger, it's going to have a lower charge density, therefore lesser ordering effect. Therefore, the decrease of entropy in water will be less by S minus ion compared to O minus ion. So it's an entropic stability difference. So the correct answer is option A. Okay, so B is out. And A is more acidic, not about the energetics. Energetics is about entropic, because energetics has to do with the neutronegativity, not the size of the ion. Right, so the correct answer is option A, which is selected already. Submit the quiz and done. All right, let's see how we did. We got question 1 correct, 2 correct, 3 correct, 4 is done, 5 is good, 6 looks good, 7 is good, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. Everything looks great. Okay. I hope this helped, and I'll see you guys in class. Bye, everybody.